also share my screen. Okay. So, as usual, whenever you have a question, please just write in the chat. And I'll stop during the lecture several times and answer all the questions that are in the chat by that time. And I'm also very sorry for the noise. There is some construction going on outside my window, so I can't really do anything about that. Sorry about the noise. So let me just go over what we saw in the previous lecture. So we talked about cryptographic hash functions, and we also talked about the properties that we want them to have. Then we want them to be collision resistant and hiding. And we saw some applications of these properties. We saw that, for example, we can use a hash as a digest, as some sort of a summary of a big file, so that we don't have to work with the big file itself. We also saw this idea of a hash as a pointer, where you use it in your data structure, you use the hash to point to a specific place. And actually the pointer is unusual in the sense that it points to a specific data, not a specific part of the memory. And that's quite nice. And we showed that you can figure out if someone is tampering with your data. For example, in this example, if the bank was changing your transactions, you can't necessarily stop it, but you can at least figure it out and know that the data has been tampered with. And the other use case that we saw was the case of using a hash as a commitment. So instead of, for example, revealing some data, you just commit that you will not change that data by showing its hash to the people first. And this was the example that we had for bidding, where N people were bidding for a specific item. And the idea was that you first reveal your hashes instead of revealing the actual bids. And then this locks you in so that you cannot change your choices anymore. And afterwards, after everyone is locked in, after everyone has committed to their choices, everyone can unmask their choices and show what the actual choices were. So now I want to talk about a completely different application, which actually combines some of the previous ideas. It combines the idea of using a hash as a pointer and also using a hash as a digest. So here's the scenario that I want you to consider. So let's say that you're a bank, and as a bank, let's say that you have branches in different places. Sorry, something is wrong with my tablet. Just a second, let me make sure the mapping is correct. Okay, so here's the scenario that I want you to think about. So let's say that you're a bank, and let's say that you have two branches. So let's say, for example, you have a Hong Kong branch, and you also have another branch somewhere else. Okay. So I don't know, for example, let's say this is the Beijing branch. Okay. And the problem that we want to solve is this. Some people might come to one of your branches, for example, come to Hong Kong branch and deposit some money. And then they want to be able to travel to Beijing and get their money from your other branch there. Okay. So again, this seems like a very simple problem. But now I'm going to make it a bit harder. What I want to do is this. I want to say that your two branches have some sort of connection with each other. And this can be basically any kind of connection line. Let's say it's the internet, for example. But the problem that we have here is that, first of all, it's not safe. So your channel is unsafe, meaning that someone else might be able to read the information that you are sending here. And the second problem that we have is that the channel is really costly. So you don't want to send a lot of information from one of your branches to the other one. But at the same time, you want to make sure that people are able to deposit in one branch and then travel to the other branch and get their money from the other branch. Now, I'm sure you've seen these kinds of things in the real world, especially before the internet existed. The idea is that the issuing branch, this Hong Kong branch, should give the customers some sort of certificate, or in many cases, it's used to be traveler's checks or something like that, that they can then bring as a proof to the other branch and show it to the other branch and say, hey, I've already paid the branch in Hong Kong this much money, and now I want to withdraw it from you. So the basic idea here is that proof follows the customer. But we also want to have some verification at least. So we want to send at least some short message from the Hong Kong branch to the Beijing branch, so that when a customer shows up with some piece of paper and says, this is the proof that I have deposited some money in your other branch, this branch can actually verify it. Right? And I'm actually not going to go through things like digital signatures right now. I'm going to try to solve this only with hashing. So what kind of idea can we have here? So let's say that the Hong Kong branch can send some message to the Beijing branch, let's say every day, but the message that they send cannot be a list of everyone who has paid them, because that's too long. So we want to send a short message. Now, how do we send a short message from one of our branches to the other one that actually proves to gives all the information that we need, that sends a lot of information? Well, we can't really do that because we are bounded by message links, right? So if I send a message of length n, I can have at most 2 to the power of n different messages that I can send. But here's the very nice solution that we have, which is using Merkle trees. And the idea is this: if you want to commit to a set instead of committing to a single message, so if you want to commit to a set of messages, you can just put all of these messages together and take their hash and send that hash to wherever you want to send it. So the simple idea here would be that the Hong Kong branch every day says, okay, I've issued, I don't know, 1,000 travelers checks for people who want to get their money in Beijing. I'm going to just put all of these next to each other and hash them and send this hash to the Beijing branch. Okay? So what we send is just a single hash of all, let's say, deposits. Okay. But now there is a problem here. So if I just send a single hash of all the deposits, and then someone shows up with a specific deposit, it's impossible to verify that this is a valid deposit, right? So the only way we can verify it now is to give everyone a list of all the deposits for the day, so that whenever a customer goes to the Beijing branch, they just have to basically give the Beijing branch a list of all the transactions in that day and say, oh, by the way, transaction number 5,000 is mine. And that's not great for privacy, right? So we don't want every customer to see every other customer's transactions as well. So in other words, the problem that we have here is that one of our branches wants to commit to a set. So not just to a message, to a set of messages. And the other branch should be able to check if a specific message is in the set. So there should be a short proof that we can give to our customer that brings to the other branch and says, hey, this deposit is in the set that the Hong Kong branch verified. But at the same time, we also need some privacy. We need to make sure that the proof that we give for every one member of the set doesn't really reveal anything about the other members of our set. Okay, so this is our scenario. If I want to write it shortly, we want to say that the Hong Kong branch commits to a set of deposits. And the Beijing branch should be able to verify membership. So if someone brings some deposit to the Beijing branch should be able to verify that it was in the set given by the Hong Kong branch. So the Beijing branch needs to verify membership. Let's give the set a name. So commits to a set of deposits, and I'll call that set S. And the Beijing branch should be able to verify membership in S. And also we want some privacy. And the idea of privacy is that proof of one membership shouldn't give us any information about another membership. Proof of one membership, let's just say, does not reveal other members of it. Now we can be much more formal about this, but there is no need, because when you see the solution, you can then come back and formalize this in a much nicer mathematical way. Okay, so we can just go back and look at the previous system that we had here, where we basically had what we would later on call a blockchain, but we had a linked list where the pointers in the linked list were hash pointers. So what I can say is that, well, what can I do? I can say my Hong Kong branch just creates a list like this with hash pointers and sends the hash of the very last transaction to the Beijing branch. Now this solves a bit of our problem, because now if a customer shows up and wants to prove that they have done this deposit here, they no longer need to give the hashes of all the previous transactions and the information about them. They only need to give us information about the transactions that came after that. But this is still not good enough for us, because it's going to contravene our privacy policy, which was that basically I don't want to see any other members of the set when I prove that one member is in that set. So the idea that was actually originally from Merkle, and that's why it's called the Merkle tree, is to use a tree. So let's say that I have n deposits. So let's put them here. Let's say this is deposit 1, this is deposit 2, this is deposit 3, and so on. Actually, let me just create a small thing here. D1, D2, D3, D4, D5, D6. So let's say I have 8 transactions. So previously what we would do was that we would just put these transactions in a linked list where all the pointers were hash pointers. Now the idea here is, let's put them in a binary tree where all the pointers are hash pointers. So I take my first deposit and my second deposit, and I put them as children of a new node. And here I just put the hash of the two, hash of D1 and D2. Oh, it's too hard to write it in there. Okay, maybe I should just do it like this. So D1 and D2. And I put this node here. Okay. I do the same thing with D3 and D4. I take their hashes and I create a new node that has the hash of D3 and D4. Okay. And it has pointers to this. Okay. And I do this for the rest as well. So I do for D5 and D6. I do the exact same thing for D7 and D8. The hashes here. And let's call these higher level ones, I don't know, let's call them E1, E2, E3, and E4. Then I repeat the same process. So I get the hash of E1 and E2, and I create a new node like this. I take the hash of E3 and E4. I make a new node like this. And at the very end, again, let's call this F1 and this one F2. I just take the hash of F1 and F2. And, oh, sorry. And this is the top of my tree, the root of my tree. Okay. So the idea is very simple. It's just the same thing that we used to do with a linked list. We're going to use hash pointers, but the only difference is that now we have a binary tree. So at the leaves of our tree, at the very bottom of the tree, we have all the actual data that we want to save. So for example, in this case, it would be the list of everyone who has deposited money in the Hong Kong branch and how much they have deposited and so on, all the information. I don't care what the details of that information is. I just create one leaf, one node for every piece of information in my set S that I want to commit to. Okay. Then I take the first two items, compute their hash, and by that I mean the hash of appending them together. And this is now my new node, which is the parent of these two previous nodes, and it's connected to them with hash pointers. Then I do the same thing for the other two, and so on. And I continue this until I have only one node. So first I had 8 nodes, then I had 4 nodes, then I had 2 nodes. And at the very top, I just have one node, which is the hash of kind of everything. And I call this the root node, or sometimes it's just called the Merkle root. And now what's so great about this? The thing that is great about this is, again, that you cannot really tamper with it. So if someone changes, for example, D5, some piece of data in my set, what does that mean? Well, D5 has changed, so the hash of D5 changes. So the hash of D5 and D6 together changes. So if they tampered with D5, they now have to tamper with E3 as well. But now if E3 changes, then F2 was the hash of E3 and something else. So F2 now has to change. But if F2 changes, then the Merkle root here should change. So basically the idea is that if you tamper with anything in this data structure, with any of the data, you have to tamper with the hash that is at the very root of this tree. Okay, and of course, all of this is assuming that our hash function is collision resistant. If you can find the collision in the hash function, you can probably do this. Okay, so this is the basic idea. And now I can answer the first question here. And the first question, or the first requirement, was that I want my Hong Kong branch to be able to commit to a large set of deposits by just sending a very short message using this costly and unsafe channel. So the short message that the Hong Kong branch can send is just this root hash, the hash of the Merkle root, the hash at the very top of your tree. Okay, so there's no problem sending this hash because we are assuming that our hash function is hiding. So if the internet is unsafe and someone else can see the hash, so what? It doesn't give them any information about the actual data. And we don't have a problem of cost because we're just sending one single hash, right? So, and a hash function had outputs of a fixed size. So the thing that I'm sending is maybe 256 bits or maybe 1024 bits. It's a very short message. And that's all the information that the Hong Kong branch sends to the Beijing branch in this case. Okay. And as we've seen before, this is enough as a commitment. Like the Hong Kong branch has now committed to all of these information, all of these deposits, and cannot change any of them without changing their commitments. Okay. But we still have more problems and we have to figure out how we can verify membership and so on. Let me just answer some questions from the chat and then I'll come back to those. Okay, so another question is, what if there is an odd number of transactions? Do you hash 3 transactions as a group? So in general, if the number of transactions that you have is not a power of 2, you can just add dummy transactions to the end until it becomes a power of 2. Right? So you can just have, for example, if I had only 5 transactions instead of 8 here, I could just add 3 dummy transactions at the end, which said that I pay myself $0.00 3 times. Okay. So another question is that, well, in order to have 2 to the power of h leaves, there are going to be almost twice as many nodes in the tree. Wouldn't this be a big tree? Yes, this would be a huge tree. But again, the point here is that I'm not going to send the whole tree from Hong Kong to Beijing. I'm just going to send the hash of the root node. So I'm just going to send the Merkle root. Okay. It would be a big tree. Okay. Okay. Someone asked, how do you signify dummy transactions? That's for you to decide. So I don't really care about the language that you use for writing your transactions, right? So, or what kind of data you want to put in each one of these D1 to D8, you can put whatever you want, and it's for you to decide how you encode that. No, so they're not the identity values of the hash function. The hash function probably doesn't have identity values at all. They're just some string that is a dummy string. Okay. So someone else asked, what's the difference between this one and the linked list idea, except for the fact that we're using a tree? Well, there is no other difference. The only difference is that we're using a tree. And at this point, it doesn't seem like it's giving us a benefit, but as I'll go through the other things that we want to do with it, you will see that this is actually much better than having just a linked list. Okay, so now let's go to the next phase of this. And let's say that someone comes and deposits some money in the Hong Kong branch. So something is wrong with my pointer again. Okay, so let's say Alice comes and deposits $500 into the Hong Kong branch, right? So this deposit would be one of the deposits here that goes into this Merkle tree. And then at the end of the day, the Merkle root is sent from Hong Kong to Beijing. But now let's say that tomorrow Alice comes to the Beijing branch, or maybe after a while, Alice comes to the Beijing branch and asks for that $500. how can the Beijing branch verify that Alice has actually deposited $500 in the other branch? So that's impossible with the information that we have right now, because the Beijing branch only knows the root hash, right? So the Hong Kong branch should give Alice some proof as well that she can present to the Beijing branch and say, see, this is the proof that I've actually paid your other branch. But we want this proof to be as short as possible, let's say. And we will later on see even better solutions for this problem. But for now, I just want to do it using hashing. Okay, so let's say that Alice's deposit is this one. Let's say it was D6. Okay. What kind of information does the Beijing branch need in order to verify that D6 is actually in this Merkle tree? Well, if Alice can just bring D6 and its parent E3 and its parent F2, then would that be enough? So let's say that Alice brings this data. It says, I have D6, I have E3, I have F2. Okay. If Alice has all of this information and gives it to the Beijing branch, can the Beijing branch verify that this information is actually correct and Alice has not tampered with it? Well, unfortunately, not really. Why? Because, well, the problem here is that if you want to prove that this information that I'm giving here was actually a child of the Merkle root, if you want to prove that the F2 was a child of the Merkle root, then you also need to know F1, right? Because that's the only way that you can compute the hash of F1 and F2. So just giving the parents is not enough. Let's do something else. And let's say that whenever Alice creates a transaction for, or a deposit, for example, D6, the proof that we give to Alice is going to be D6 itself, as well as the parents and all of the ancestors, basically, of D6. So I start at D6 and I go up the tree until I get to the root. And I give all of this information to Alice. So I give D6, E3, and F2. And remember that E3 is just the hash of D5 and D6. Okay. What else do I need to give to Alice? Well, I also need to give the information about siblings of all these ancestors. So since I have given F2 to Alice, I should also give F1 to Alice. And this is so that when she goes to the bank in Beijing, they can verify that, okay, F1 and F2 are the children of this Merkle root. So they are both valid. And then they don't need to verify anything about the subtree that is on the left with F1. They continue with F2. And they want to be satisfied that, okay, E3 is actually a child of F2. But the way that they can do that is by knowing E4 and E3. So we have to give E4 to Alice as well. And finally, they have to be satisfied that D6 is a child of E3. But the way that they can do that is if Alice knows D5. Okay? So if I just give Alice the parts of the tree that I highlighted in green, then Alice can bring all of this information to the Beijing branch and say, hey, I made this deposit D6 in your Hong Kong branch. And here's the proof. And the proof is basically all the parts that I've shown in dark green here. Now, the Beijing branch has already received the Merkle root from the Hong Kong branch. So they can trust this one. They can trust the Merkle root. They're sure that the Merkle root is fine. Because they trust the Merkle root, and because Alice is giving them F1 and F2, they can just compute the hash of F1 and F2 and see that, okay, F1 and F2 are really the children of this Merkle root, and this hash matches. So this proves to them that Alice has not tampered with F1 and F2. Now, they don't need to have any more information about F1 and its children. That's irrelevant. But they need to they need to be convinced that E3 is a child of F2. And again, they get convinced of this because Alice gives them E3 and E4, and they can just compute the hash of E3 and E4, and they're convinced that, okay, both E3 and E4 are children of F2. Again, they don't care about E4, but they want to make sure that D6 is a child of E3. So they just need to hash D5 and D6, which is given to them by Alice. And then they can see that it's equal to E3, so they can be sure that this part is not tampered with. So what does all of this give us together? Well, basically Alice could prove to them that this particular deposit D6 was actually in the tree that was created at the Hong Kong branch. And the Hong Kong branch didn't need to send the whole tree over the internet. They just needed to send the Merkle root. Okay. Now, we have a bunch of questions here. So, and I'm going to get to this, and they have actually found a really good problem here. So someone says now Alice can pretend that she has made deposit D5 as well. Well, the way that we can fix this is that we can also have the identities of the depositor built into the deposits. So here, as I said, you can think of each one of these as a deposit or as just some piece of data. And this piece of data can give you anything, like any kind of information that you need to prove when you get to the Beijing branch, right? And so this information can be that Alice with the following identity has put $500 here. So in this case, if Alice proves both D5 and D6, she can only claim D6. But there is a worse problem actually here. And the worst problem is with privacy. So we talked about this thing, this third property, that we want to make sure that whenever we prove membership of one particular piece of data, for example, when Alice proves that the deposit D6 was actually in the tree, this shouldn't reveal anything about other pieces of data. So it shouldn't reveal anything about D5. But now we are revealing D5 as well. And actually the Hong Kong branch is giving Alice D5 as part of the proof that Alice is going to show to the Beijing branch. So the way we can fix this is that we can just do one more level of hashing. So instead of putting D1 here, I can just put the hash of D1. Okay. Instead of putting D1 here, I can just put the hash of D1. And then let's say that D1 itself is here. And similarly, I can do this with all of them. So here in my tree, I will just put the hash of D2. Okay, and so on. And then this one would be the hash of D1 and the hash of D2, of course, because each node basically has the hashes of all of its children. So I'm not going to update all of this because it's going to take a while. But generally, the idea is that don't put any of the actual information in your Merkle tree. Just put the hashes at the very beginning. So then what happens again is that what Alice can prove to the Beijing branch is that the hash of her deposit is in the tree that Hong Kong branch has sent over, right? And after she can prove that, then she can give the actual deposit information as well. And then again, it's just one more level of hashing. And the Beijing branch can just compute that hash and make sure that it matches the hash that was actually in the set. So the idea here is that instead of having a set of deposits, S, we say that S is a set of hashes of deposits. So that's just one minor detail there. Okay. Okay, now let me just look at the questions again. So one really nice question is, how is this better than just going through the linked list and checking if a transaction exists? Because here Alice needs to show us all the other data as well. Yeah, okay. So the important point here is that how much information do you want to give to Alice? So how long is the proof that your customer has to carry from Hong Kong to Beijing? So we have basically two transfers of data, and we want to optimize both of them. One is this transfer over the internet, which we said we assume it's unsafe and very costly. So we wanted to minimize it as much as possible. And the solution was that we just sent the Merkle route. But the other thing that we want to optimize is how much information each proof has to contain. Like how long is each proof? If Alice wants to go to Beijing, like what is the length of the proof that she has to provide to the Beijing branch? Okay. So in this case, the problem was that the length of the proof would have been linear in the number of transactions. So if Alice wanted to prove the existence of this transaction, she had to provide all the transactions, the hashes of all the transactions from here all the way to the last transaction. And that was awful, right? So the length of the proof would have been linear. But now here, if you think about it, this is a balanced binary tree. So if you have n pieces of data in there, the height of the tree is logarithmic. And basically the number of different pieces of data that Alice has to provide there, the number of different nodes that Alice has to include in her proof is just twice the height, right? Because at any given height, we need 2 of the nodes. So in total, the length is logarithmic. So if you have n transactions and Alice wants to prove that a particular transaction is in there, she only needs to provide a proof of length order log n. Okay? And of course, it can be verified. And finally, using this final trick that we hash all the data before putting them into the leaves of our tree, we also have the privacy that we wanted to have. So if Alice proves the existence of D6, basically what she has done is that she has proven that the hash of D6 is in this particular tree, right? And of course, to do that, she has provided the hash of some other deposit D5, but having the hash of D5 doesn't really give us any information about D5 itself. That's the hiding property that we had. So we also have privacy here. Okay, so let me look at questions one more time. Okay. Okay. So there is a question that if Alice gets hash of D5 and D6, which other info does she need? Well, basically what we said here is that instead of putting D5 here, I will just put the hash of D5. So let me just try to erase this. Okay, so this is the hash of D5, and this one is now the hash of D6. So she needs D6 itself. She needs hash of D6. And then she wants to prove that this hash of D6 is actually in the tree that was sent over, right? So she needs to prove the whole path from the root to this leaf here. And in order to prove this, she needs the siblings at every level. So first of all, in order to prove that F2 is in the tree, she needs to have F1, because then the Beijing branch can just compute the hash of F1 and F2 and see that it's the Merkle root. So this proves that F2 is in the tree. Then the next step is that she wants to prove that E3 is in the tree. So she has to have E3 and E4. This proves by just hashing that E3 is in the tree. Then she wants to prove that hash of D6 is in the tree. So she just needs hash of D5 and hash of D6 to prove that. So generally at every level of the tree, she needs two different values, two different nodes. Okay. So another question is, if Alice's transaction is the first of the day, how does Alice get the hash of other nodes? Well, she doesn't. She just has to wait. So let's say this is like a very weird situation where everyone is in Hong Kong one day and they all make their deposits and they all get their proofs a few hours later, let's say, and then everyone goes to Beijing and wants to get those things back. So again, the properties that we want here is not that everything goes smoothly, that everything is fast or anything. We just want to make sure that the commitment is short. So the message that one branch has to send to the other branch is short, and that membership can be verified, and that the length of the proofs of memberships is short, and finally that privacy is preserved. So this is a common theme throughout this course, and you will see a lot of these things. Like we talk about a lot of unrealistic scenarios and we try to solve a lot of unrealistic problems. But then the idea is that at the end of it, we will put all of these things together and have some real world blockchain and cryptocurrency that will solve all of these problems at the same time. Okay. Another question is, so the Beijing branch does not know the real deposit of customers? No. The Beijing branch only knows the Merkle root. And so the only thing that the Beijing branch trusts is that the Merkle root that they have received from the Hong Kong branch is correct. And then every customer can come there and provide a correct proof. And if they provide a correct proof, they will be paid by the Beijing branch. Okay. Oh, another nice question here is, in this case, does the Beijing branch need the height of the tree as well? And actually, no, they don't need the height of the tree. Because think about it, it's like, suppose again that I want to prove that this particular node is in the tree. What do I have to do? I start from the top and I tell the Beijing branch, hey, first I'm going to prove to you that F2 is in the tree, and here's the proof. The proof is F1 and F2. You can hash them and be sure that F2 is in the tree. Okay, now that I have proven to you that F2 is in the tree, I can prove to you that E3 is in the tree, and so on. I can just continue this forever. So the Beijing branch doesn't need to know the height of the tree, because at some point I would just say, okay, now this thing that I proved exists in the tree, this is the hash of my deposit, and here's the actual data of the deposit, and you can hash it and see that it matches. So the proof doesn't need the length of the tree and the depth of the tree, and actually the tree doesn't have to be a balanced binary tree. It's just nicer if it is, but you can generally have any kind of binary tree there. Okay. Another question is about agreeing on the same functions. Yes, we just assume that everyone is using the same hash functions. Another problem is about double spending. So what happens if Alice deposits $100 in Hong Kong and then repeats this? Again, we are not considering a realistic scenario here. So the scenario that we are considering here is that there is a specific day that everyone is depositing money in Hong Kong, and there is a specific day later on that everyone is going to get their money in Beijing. And in this particular case, she cannot prove her deposit twice, because, well, the Beijing branch can just keep track of all the deposits that they have fulfilled. So if they fulfill a deposit D6, they just keep it there. And if someone else comes again and proves D6 again, they say, okay, good job, the proof is correct, but I have already paid this deposit, so I'm not going to pay it again. So another question is that if we had a linked list, the Beijing branch still needed just one hash from the Hong Kong branch. That's true. but the proofs would become much longer. So every time that Alice wants to prove that she has deposited some money, she might have to give n different hashes in order to prove that. And the good thing here is that the length of the proof is also logarithmic. Okay, great. So Merkle trees show up in all sorts of applications. And so we will see them a lot later on. This was like just a very unrealistic scenario of using them. Actually, one real scenario other than blockchain where we use Merkle trees is in Git, for example. So if you work with GitHub, the way that the files in a specific commitment or in a specific commit in that language are saved is using a Merkle root as well. So that basically if you have different collaborators working on the same repository, everyone can be sure that the history has not changed or that specific parts or specific files have not changed without having to verify everything and just doing all the comparisons. So that's also a nice use case. And so the analysis here, I'm just going to repeat what I said. Commitment using a fixed size hash. So the commitment is really short. So it's just one message, one short message that the Hong Kong branch sends to the Beijing branch. And then each proof takes order log n bits to prove anything. Or actually, let me just say order log n hashes, because, well, we don't know how long the hashes are. And of course, we also have perfect privacy. And this perfect privacy is assuming that the hash function is hiding, right? And we have no double spending, so you cannot claim the same deposit twice, because the Beijing branch can just keep track of the deposits that they have fulfilled. And if they see a hash for a second time, they just say, I have already done this, I'm not going to do it again. Okay? Now, but let's just talk about a slight extension of this idea. And let's say, again, forget the use case, and let's say that what we have is just a set S of different data, of different strings. And what we wanted to do was that we wanted to be able to verify or to prove that a specific string is in that set, right? And we wanted to have this privacy as well. So what happens if I want to also prove absence of data? Okay. So what happens if I want to somehow, again, in our example, this doesn't make much sense, but let's just consider it theoretically. What happens if I want to prove to the Beijing branch that a specific transaction or a specific deposit has not happened? I want to prove to them that a specific string is not in this tree. How can I do that? So you see, proving membership was easy. Proving membership was that you just go through the tree and give the hashes of all the ancestors and all of the siblings of the ancestors, and that works well. And you can prove to someone that a specific data is actually in the tree. But what if I also somehow need to prove that a specific piece of data is not in the tree? What can I do then? And actually, this is also quite easy. And the solution is what we call a sorted Merkle tree. And the idea is very similar. The idea is that, again, we have all these hashes at the leaves. So I'm too lazy, so I'm just going to put 4 now, hash of D4, and then we have a node here, another one here. Okay. I'm really bad at drawing, sorry about that. And let's say that I have another node here. So I have this tree. And I additionally put this constraint that all of these numbers should be in sorted order, or if they are data, well, we can just sort them alphabetically or lexicographically. So the additional requirement that I put here is that hash of D1 should be less than, sorry. Well, actually, yes, that's correct. Hash of D1 is less than hash of D2. It's less than hash of D3, and so on. So I have a Merkle tree, but the only difference with the normal Merkle tree is that all of my leaves, all of the hashes at my leaves are in a sorted order. Okay? So now suppose that I want to prove that some data X is not in the tree. Okay? What can I do here? Well, I can just find the leaf behind X in lexicographic order and the leaf after X. So let's say that X should have appeared, for example, here. If we had an order, maybe X was between hash of D3, hash of X, and hash of D4. Let's say this is where X should have appeared. Now, in order to prove that X is not in this set, all I have to do is that I have to prove that this D3 is in this set and D4 is in this set. So I just have to provide this node, their parent, of course, its sibling, and this one, right? And because they are immediately after each other, because I'm proving that there's also no other leaf between these two, this proves that X was actually not in my set. And in this case, again, it's easier to use balanced binary trees, because another thing that you have to notice here is that whenever we are proving that some particular data is actually in the tree, we are not just proving that the data is there, we are also proving its location in the tree, right? Because when I proved here that D6 is in this tree, I was actually proving that if you go right from the root and then left and then right, you will get to D6, right? So if I can prove that if you go the same way, but just at the very end, you go left, you get to D5. And if these are sorted, then you can be sure that nothing is between D5 and D6. And this is the way that we can show that a particular item is not in our set or in our tree. Okay. So, okay, so there was a question there, but it's already answered, so good job. Any other questions about how a Merkle tree works? Okay. So again, as we go on with this course, we will get less and less theoretical. So this is probably, this and the next session are probably our most theoretical sessions. And then we will just ease into using these things only. So later on, I will not really talk about Merkle trees anymore. The only things that I will say is that, okay, we have a set, we want, for example, we have a set of transactions. We want to prove that a particular transaction is in that set. And we just assume that we know how to do that. And when you implement it, it would be using a Merkle tree. But when we get to the cryptocurrency part and when we get to the blockchain part, we wouldn't really care too much about how these things are done. So we will have a much more high-level view of the things later on. Okay, great. So this ends the things that I wanted to tell you about our first cryptographic primitive, which is hashing. So these are all the things you need to know about hashing in order to make a blockchain, and then we will later on come back to that. So the next problem that I want to talk to you about is what we call symmetric encryption. And here's the scenario. The scenario here is much simpler. The scenario is that we have two people. We have Alice here and Bob here. And they have some channel of communication. And again, let's say this channel can be the internet or maybe a phone line or whatever, any kind of communication. And this channel is not secure. And what I mean by that is that someone else can basically see all the messages that they send and receive. And we usually call that someone else Eve, because what they do is eavesdropping. So Eve can see all the messages that go on between Alice and Bob over this channel. But now Alice and Bob want to communicate with each other in a secure way so that Eve cannot find any information about their communication. Okay? So here's the definition if I want to write it a bit more formally. Okay, no, actually, I'll come back to that. So you see the situation. This is a very common situation. We have it all the time over the internet. If let's say you want to browse a website and you have a password on that website and you want to send your password to that website, you don't want your internet service providers and all the hubs in between to see your password, of course, right? And this is the solution to this is what you have all seen probably before. It's called encryption. So the idea is that Alice first encrypts her message. So let's say Alice encrypts her message M to get some other message. Let's call it E because it's encrypted, and sends this encrypted E to Bob, right? And of course, what happens here is that Alice had the message M. She also had the encrypted message E. Actually, let me just use small m just to be consistent. So she knows these two things. She sends E over to Bob. So Bob now knows the encrypted message. And Eve also learns about the encrypted message, right? And then the idea here is that Bob should be able to decrypt it. So Bob decrypts E to get M. And then we will be happy because both Alice and Bob know M, but Eve only knows E and doesn't know anything about the original message. So Eve has only seen the encrypted message. Now, we have to be a bit more precise about this and actually talk about what this means. Like, why is it that Bob can decrypt the message, but Eve cannot? So the way we can be more formal about this is that we can do this. I can say that Alice knows some function, and this function is called, let's say, enc. And what this function does is that it encrypts. So it gets a message, which is, remember, just a series of zeros and ones, a string, and gives us another string. Okay? And we should also assume that Bob can decrypt it. So Bob knows another function, And we can call this function dec for decryption or decrypt. And this one also gets a coded message, an encrypted message now, and returns the original message. And of course, what we want is that we want to say that for every initial message, if Alice first encrypts that message, oh, sorry, this should have been Sigma star. So for any initial message, if Alice first encrypts it and Bob then decrypts it, the result should be the original message, right? So the decryption function should be kind of like an inversion of the encryption function. Now, what else do we need? We also want to be sure that Eve cannot do this. So what I want, other than this, is that someone who knows the encrypted message should not be able to get the decrypted message, right? So if Eve knows only the encrypted message, encryption of M, but not that function, then now we can have different definitions of security. So one definition is that we want it for Eve to be impossible to compute the original message M. Or I can go much further and I can say that it should be impossible for Eve to find out anything about the original message M. So not only she cannot know the original message with certainty, but she can't even know, for example, a small set and say, okay, the message is one of the messages in this set. She shouldn't even be able to have some sort of probability distribution that tells her that it's very likely that the message is one of the following gets, and it's very unlikely that the message is something else. So, but again, I just want to keep it very simple. So if Eve knows only the encryption, but not the function that is used for decrypting it back, then it is, let's say, impossible for Eve to compute the original message M. Okay. Now, so what I want you to think about right now is that what are the secrets and what are the public parts of this protocol? So of course, M itself is a secret. So I'm just going to show all the secrets in red. So this secret should be known only to Alice and Bob, but not to Eve. Okay. And additionally, we have this encrypted version E, and this is public knowledge. This is what we send over our channel, over the internet. So it's fine if Eve knows this, right? But what is the problem that we have with this definition? The problem is that, well, we have to also talk about these two functions, the two functions encryption and decryption. And we have to say which one of them are actually public knowledge and which one of them are secret. So the encryption function does not really have to be a secret, right? So even if Eve knows our encryption function, as long as she cannot invert it, as long as the encryption function is hiding, she can't figure out anything about our original message. So for example, if my encryption function was a cryptographic hash function, then it doesn't matter that Eve knows that I'm using SHA-256, she cannot really invert it. Of course, the cryptographic hash function is not a good function to use here because we want to be able to decrypt it ourselves. So we want this decryption function to be a secret, and we want it to be hard to find, right? But this is a bit hard to construct, because if you think about it, we're just saying that we're changing our functions all the time. And we don't want the security of our cryptography and of our messaging to be based on changing functions, basically changing the algorithm that you use for encryption or decryption. Instead, it's much nicer if our functions can have some secret parameter, and we can just change that secret parameter. And this is what we call a key. So a key is generally any kind of secret. Okay, so let's say that a key is just a string, so let's call it K, that is supposed to be secret. Okay, so I can just add the key here. So I'm assuming that both Alice and Bob also know some secret K, and no one else knows that. If this is the case, then I can change my definitions a little bit here of encryption and decryption. And what I can say is that, okay. What I can say is that the encryption function actually takes the key. So I don't have just one function, but I have one function for each key. And this function gets some message and encrypts it to some other message. And the decryption function also gets the key and decrypts the thing back. And the idea is that if we use the same key, after encrypting with the same key and decrypting again with that same key, we should get the original message that we have. And now, what do we want this attacker Eve to know? So I want Eve to know basically everything. So she, of course, sees this encrypted message E, which is sent over the network. So this. And let's say that she also knows my encryption function. So I'm not going to hide my encryption function. I'm going to publicly say, this is how I encrypt. And let's say that the attacker also knows my decryption function. So again, I'm not going to hide the algorithm that I'm using. I'm just going to say, this is the algorithm that I use for decryption. This is the algorithm that I use for encryption. And this is the encrypted message. But the only thing that I want to hide is that the key should be hidden. So, but not K. If Eve knows the encrypted message, the encryption algorithm, and the decryption algorithm, but she does not know the key, then it should be impossible for her to compute the original message. Okay? So this is the property that I want to have. And if I have a bunch of functions like this, so if I have a family of encryption functions and a family of decryption functions, one for each key, and if they have this nice property that decrypting an encrypted message gives me the message back, and also without the key, no one can decrypt, then I call this a symmetric encryption system. And I call it symmetric because if you look at the knowledge that the two sides have, that Alice and Bob have, it's symmetric. They both know M, they both know K, right? Of course, at the beginning, only Alice knew M, but after she sends the message, Bob can also know it. Okay. So we now have several problems. First of all is, how do we define our encryption and decryption algorithms so that everything is safe? And that's what I'm going to answer now. But then the next problem that we will have is that we are assuming that both Alice and Bob have this shared secret key K, right? So they both know some value that no one else knows. And that's why they can communicate with each other, because they can use that value in order to encrypt their messages. So another problem that we will actually address in the next session is, what if we don't have this shared value? How can we create this shared value? But for now, let's just assume that we have this shared key K between the two sides. And Alice wants to send a message to Bob. So here's what I'm going to say. I'm going to say that suppose the message and the key have the same length. So suppose that both the message and the key are n-letter words, right? What I can do is this. I can just take the XOR of the two words. So for those of you who are not computer scientists, and this might be new to you, so suppose that my message is something like this, and my key is something like this. When I XOR them, I just check if the two digits are the same. If they are the same, I put 0. If they're different, I put 1. So 0 and 1, when I XOR them, it's 1. 0 and 0 is 0. 1 and 1 is 0. 1 and 0 is 1. 0 and 1 is 1. So this is the XOR operation, and we will show it with a circled plus. So it's basically addition in base 2, except that we don't carry anything to the higher values, okay? We don't have carryovers here. So if my message is a string of length n, if my message is a list of n zeros and ones, and my key is also a string of length n, I can just encrypt my message by taking this XOR. So I can just say encrypting using key k of message m gives me the encrypted message m XOR k. And actually, in this case, the decryption is super easy. So what is the decryption? Can you tell me in the hash? In the, sorry, chat. I said hash so many times, I'm just used to it. Okay. Yes. So if I want to decrypt something, let me actually not call it M this time. Let's say that I have some E and I want to decrypt E. I just XOR it with K again. And why does this work? Well, because if I want to have this property that decrypting after encrypting gives me the original message. So let's see what happens. If I decrypt with K, the message that was encrypted using the same key K, well, this part was M XOR K. That's what the encryption did. And then the decryption does another XOR with K. But one of the properties of XOR is that if we XOR something twice, it cancels out. So this would just be M. So if I start with a message or string M, and I first encrypt it with a key K, and then I decrypt it with the same key K, I will get the same message. So we have this really nice property now that encryption and decryption are inverses of each other. And actually, this is really nice because our encryption and decryption function are actually the same function, right? It's just XOR it with the key. But why does it have this extra property? So what happens if someone is just eavesdropping over our internet connection and they see the encrypted message that was transferred? So let's say, here's the analysis. Let's say Eve sees the encrypted message E, which was the result of encrypting M using K. Okay? And we also know that Eve does not know K. Okay? So why is it impossible for her to compute M? Well, actually, you can give a very straightforward mathematical proof. If Eve can compute M, then she can also just take its XOR with E and find K. So this contradicts the idea that Eve didn't know K, right? But another more direct way of seeing this is this. So consider all strings of this possible length. So if my length is N, then I have 2 to the power of N possible strings, right? So, or in other words, I have 2 to the power of N possible messages. I just know that this message M has this length, but I don't know which message it is. And for each one of these messages, there is actually a key such that if I use that particular key in my encryption, I will get the value that I could observe here. I will get E. So in other words, if again, I want to be a little bit mathematical, I can say that for every message M, there exists some key K such that when I encrypt that message with that particular key, I get E. And E was the encrypted message that I could observe on the channel on the internet, right? So in other words, if I don't know the key, I don't know anything about the message, right? Because I don't know which K it was used, and any possible message could have been the original message that Alice wanted to send to Bob. So as long as I don't know anything about the key, I don't know anything about the message. And this is what we actually call perfect secrecy. And this idea of using XOR, this crypto system is called a one-time pad. And we call it a one-time pad because it's only safe for sending one message. So if you want to send a second message, you'd better change your key. Because if you keep sending more and more messages with the same key, then an eavesdropper, Eve, can just figure out like what are the patterns in these messages and can decrypt them. For example, here's another example here. So let me be very fast here because we're out of time. Do not reuse your keys. Why? Because if you have two messages, M1 and M2, and you have the same key K, and you want to send this over, what do? You first encrypt one of them, so M1 XOR K, and send over, and then you encrypt the other one, M2 XOR K, and send it over. And now the eavesdropper who was in between can see both of these things, can see both of these numbers, M1 XOR K and M2 XOR K. And what she can do is that she can just take the XOR of these two. So she can take the XOR of the first one with the second one. Sorry. And again, in XOR, the repeated stuff cancels out. So the two Ks cancel out, and you will just get M1 XOR with M2. So this is not the same as one of the messages, but now we could cancel out the key, and now we have the XOR of two messages. So we can do some sort of statistical analysis and try to figure out what each message was. Or if we have more messages, actually this gets easier and easier. Like if you have 10 different messages and you have all these pairwise XORs between them, you can pretty much do a statistical analysis and just decrypt it, especially if you know that, for example, your original messages are strings written in English, right? So we don't want to do this kind of thing. This actually leaks information. So you should never reuse your keys in this case, and that's why we call it a one-time pad. And the last point that I just want to say, and I'm 2 minutes over my time already, is that only keys matter. So the only thing that we keep secret is our key. So the encryption and decryption algorithms are not secret. And this is a really important thing that is actually quite recent. It only happened in World War II. Before that time, the way people sent messages and ciphers to each other was that they just relied on this idea that the other side like knows a process of deciphering that no one else knows. So the algorithm used to be the secret. But now in all of the cases that we will see later on, only the key is the secret and all the algorithms are public. Everyone knows all the algorithms. So this makes it also much easier because you have to only keep a short secret, which is your key. Only keys are secret. Okay, so that's all for this session. In the next session, we will talk more about how to actually create these keys. But for now, have a great day. You can leave and I will stay back and answer the questions in the chat. Okay, seems there are no questions at the moment. So if you have any questions, please ask in the chat and I will answer them.